Hello, my name is Elio Maia, and I'll be describing a numerical investigation carried out in the scope of my PhD thesis on the general method for the fire design of web tapered beams. This will be the overview of my presentation. It's general knowledge that the mechanical properties of steel degrade at elevated temperatures, and so Part 1.2 provides simplified methodologies for the out-of-plane stability check of steel members. However, these fire design rules are limited to uniform members. When it comes to tapered members, the out-of-plane stability check at normal temperature is done with the general method. However, this methodology is not widely validated, and also no specific guidelines are provided for its adaptation to fire in Part 1.2 of Eurocode 3. However, the authors have shown in the past that the general method adapted according to the guidelines of Part 1.2 is conservative for tapered beams, and a calibration has been proposed, and a calibration has also been proposed for tapered columns. This investigation is part of a research effort which started with a very simple question. Are normal temperature methodologies applicable to the design of tapered members in fire? So we started by adapting normal temperature methodologies to fire from the literature and the norm, and although overly conservative, the general method emerged as the one with the most potential to be calibrated. And so we proposed a preliminary calibration which had some flaws, which I'll go over later in the presentation. And this brings us to the present work, which tries to improve upon this preliminary calibration with a more extensive parametric study. And since this is a work, an investigation subject in the early stages of development, it is always evolving, and improvements to this work have already been made, and they are currently under review. If we zoom out to the whole picture, the whole research line, we have shown the progress of tapered beams, but we have also proposed the calibration to tapered columns, and we are currently working in interaction factor for tapered beam columns, with the ultimate goal of my PhD thesis being to reach a unified calibration of the general method for the three types of members. The general method treats the buckling resistance of beams outside the range of clause 632, and the stability is verified with the following condition, which takes into account the out-of-plane reduction factor and also the minimum load amplifier for the in-plane design loads. The method is adapted to fire by considering the degradation of steel material properties with temperature, namely the yield strength and the Young's modulus, and the load amplifiers are then calculated. The load amplifiers are introduced in the formula, and the final criterion is reached. It should be noted, however, that this is done with the buckling curve of Part 1.2, which is the same regardless of being a column beam or regardless of the geometry, which is a very clear limitation. The fact that the adapted general method only has one buckling curve was the main motivation behind the preliminary proposal by the authors, which tried to explore the correlation between the slenderness plateau with the bending diagram and the taper ratio, and we have reached a very expedited proposal. However, it had two main limitations. The first is that the parametric study was not extensive enough, and most importantly, that it was discontinuous for intermediate bending diagrams. The numerical simulations were done in Saphir using shell finite elements. The mesh was chosen based on sensitivity analysis with 12 divisions on the flange, 18 divisions on the web, and 100 divisions along the length. Fork supports were modeled by restraining the lateral displacements of the web and also the vertical displacements of the bottom flange. The loads were applied by means of nodal forces, with high thickness end plates being used in order to avoid numerical problems. Also, in order to establish a comparison between numerical results and simplified methodologies, a uniform temperature diagram was adopted. The material law follows the stress-strain formula of Eurocode 3, and the residual stress pattern for welded cross-sections was adopted. The geometric imperfections were introduced in the model by changing the nodal coordinates of the member in order to reach the worst-case scenario in terms of resistance, and their shape was given by linear buckling analysis with cast-M. Also, the usual combination of local and global modes was performed, and the amplitudes of the imperfections were chosen as 80% of the fabrication tolerances. The numerical cases were generated, ran, and analyzed using FEM Studio, which incorporates 4 tools developed in the University of Aveiro. The parametric study was made up of 4 main cross-sections, which were equally distributed in terms of H over B ratio, and an additional class 4 cross-section. 6 bending diagrams were considered, and an additional boundary condition with a lateral restraint on the upper flange at mid-length was also added, to a total of more than 21,000 simulations. This slide shows the same member subjected to different support, different boundary conditions, to the left laterally unrestrained and to the right laterally restrained, showing distinct lateral torsional buckling behaviors. So this, in line with the previous conclusions by the authors in previous works, the adaptation of the general method is overall conservative, although some residual points were unsafe. Regarding the preliminary proposal, it has the ability to more or less predict the out-of-plane behavior of laterally unrestrained members. However, distinct out-of-plane behavior is shown to the chart on the right for laterally restrained members. And in this case, unsafe data points are observed. It should also be noted that since the methodology is discontinuous in terms of intermediate bending diagrams, it does not include these diagrams. In order to more accurately predict this distinct out-of-plane behavior, the proposal was done in 2 steps. First, the slenderness plateau now considers 3 additional coefficients. Coefficient P, coefficient Q, which take into account the boundary conditions, as well as the bending moment diagram. Also, an additional coefficient N was introduced to consider the cross-section classification. The imperfection factor was also calibrated with a modified version of the effective section factor from Couto 2016. With this new calibration, the general method now produces safe results for tapered beams, and the methodology now takes into account the distinct out-of-plane behavior of laterally restrained beams, and most importantly, it now covers intermediate bending diagrams. Concluding, this work is part of a research effort that's started by adapting the general method, showing that it was conservative for tapered beams, and then proposing a preliminary calibration for these members. However, some limitations have been identified, namely the representativeness of the parametric study and its discontinuity in terms of loading conditions. So, this work implemented a more extensive parametric study with a new boundary condition, and we have reached an improved calibration for the general method for the fire design of tapered beams. In terms of future developments, the goal is to simplify the slenderness plateau calculation and also to propose a separate factor for the secondary boundary condition in order to improve scalability, and this is already done and currently under review. Thank you for your attention.